we're going to continue talking about rigid bodies. We're going to talk about the rigid body kinematic differential equation and using either Euler angles or the rotation matrix. And if there's time, get to some pre-rigid body dynamics. So let's just get into it. What do I mean by rigid body? There's lots of different pieces to rigid bodies. That's why we keep kind of jumping around. But rigid body, think of here's a rigid body. And it's, if we were to follow the path of some point on it, some reference point that we're following, maybe it's the center of mass as it moves around. And we have an inertial frame. If we were to follow the path, let's call this the origin O. If we were to be following the path of that, we want that as a function of time. That would be the translational dynamics. So if we use the usual Cartesian coordinates, the translational kinematic equation, differential equation, would be x dot, y dot, z dot. Right, this is x, y, z as a function of time. To get that as a function of time from the dynamics, we could set up, well, it's kind of lame that I'm writing a matrix, but it's just to show you how different things are when we go to rigid body kinematics. So here we'd be solving an ODE, which got x dot, y dot, z dot on the left-hand side. And on the right-hand side, we've got the x velocity, the y velocity, and the z velocity as a function of time. And you would get those, right? You would get how these evolve from the translational dynamics. So from the Newton's equation. Oops. So we'd get these from the dynamics. And why do I say that? Well, because you could write the dynamics instead of F equals ma, you could write it as m v dot. So how does the velocity evolve? That's the acceleration. It equals the force. Move the force over, move the mass over. And so this is the dynamics. So you've got the dynamics. How does v evolve in time? And then this is basically how does the position evolve in time. So you need to have the two. You have the dynamic equations and the kinematic equations. For rotations, it's different. So what if we were trying to use the Euler angles? Well, we've got lots of different things going on. So let's say here's the, I guess that wouldn't be how it moves. We would have this is the velocity, right, of this point. We've also got an angular velocity. So how some body fixed frame is instantaneously spinning with respect to an inertial frame. That's going to be changing in time. So we want to go from this angular velocity to angular coordinates. Just like in this translational kinematic differential equation, we're going from the translational velocity to translational coordinates. And it's just not as straightforward. So if our angular velocity written in components, omega 1, omega 2, omega 3, and because it's more convenient, we often write these components with respect to a body fixed frame. There's some relationship between, let's use the 3, 2, 1 Euler angles, yaw, pitch, and roll. How does yaw, pitch, and roll, how do they evolve? And it will be some non-trivial matrix. Up above, this is the identity matrix, so that's trivial. we usually don't even write that as a matrix. But here, all of the different directions kind of get mixed up with each other. So there's a relationship between them. So this is how you would write the translational. This is the the rotational. This is the rotational kinematic differential equation. And we have this is an unknown right now. We'll find it, unknown 3x3 matrix. And its entries are going to depend on Euler angles. Okay, so we want to get that. Because once we know how the Euler angles evolve in time, then we know how the frames evolve in time, because then if you have the Euler angles as a function of time, say yaw, pitch, and roll, then you could populate the entries of that rotation matrix. If you remember the rotation matrix that relates the two frames, actually, I think I have a version of it that I can just show you. Where are we? We're in week 7. There we go. Yeah, this is it. So this is the 3x3 matrix using the yaw, pitch, and roll Euler angles. So whatever your instantaneous Euler angles are, then you would put them in here, evaluate these sines and cosines, and this matrix is the matrix that relates the body fixed frame to the inertial frame. So it tells you the orientation. Okay. Sometimes people just leave it as, well, once you know the Euler angles, you're fine. But if you want to do any kind of calculations, or especially visualization will need this rotation matrix to rotate a body and animate it. Okay, so we're going to go through this exercise of finding this unknown rotational kinematic differential equation matrix for the case of the 3x3 Euler angles, or the three Euler angles yaw, pitch, and roll, which, if you don't remember, let me show the, I think I've got the video somewhere. Remember these? So this is showing yaw, positive yaw, it's to the right, positive pitch, then positive roll. So you look at those instantaneous. I've got a little space shuttle model, so I can do, you know, yaw, pitch, roll. Maybe you're thinking, what's the space shuttle? Well, when I was a young boy, we had this shuttle going into space, and it was supposed to be shuttling somewhere. But when it first was flying, it wasn't shuttling to anywhere except space. It was supposed to be shuttling to the space station, but it went up for like 20 years without having a destination. So now we still have the space station, but we no longer have a shuttle. Now we've got private companies doing things. Okay, so we're focusing on trying to get this. And we could do it for this yaw, pitch, and roll. Okay, so we're going to construct that 3x3 matrix. And if you remember from last time, we said there were actually 12 different sets of Euler angles. So this is the matrix we're going to find is only true for the yaw, pitch, and roll, which is also known as the 3-2-1 convention, because you first rotate about the number 3 axis, then the new number 2 axis, and then the new number 1 axis. So how do we do this? Well, I'm going to be drawing kind of a sketch of the rigid body, but I'm not going to try very hard. So it's this blob thing, and we've got the I'll write the inertial direction. So we imagine that initially the body frame and the I-frame are aligned. Okay, and this is E1, E2, E3 is the inertial frame. I write initially because this is only just conceptually to write down the rotation. Initially, the body frame and the inertial frame or I-frame are aligned. Okay, and then we do a rotation to go to the kind of the next intermediate frame. We go to a new frame called the A frame, and that's through a rotation about the number 3 direction. So this E3 equals A3 because we're rotating about it. We're rotating using the right-hand rule, my thumb on my right hand pointing in the direction of the axis, my fingers are curling in the direction of the rotation. And this rotation angle is psi, and the rate at which we're rotating is psi dot. So we will say, this is how we'll write it, the angular velocity of this kind of made up intermediate frame, an A frame with respect to the I frame, that angular velocity vector is psi dot, that's the rate of rotation, and the axis is, we could either write A3 or E3. I'll write A3. So that is that rotation. So this is taking us from the, if you remember from last time, right, we had this compact way of writing, this A hat stands for A1, A2, A3 written as a column vector. This equals the rotation matrix I to A times the E unit vectors. And this was, we also had the notation R. That means just rotation about the number 3 axis through an angle psi. So this was shorthand for, now I'll write the full thing out, A1, A2, A3, these unit directions, equals cosine psi, sine psi, negative sine psi, cosine psi, 0, 0, 1. This is a rotation about the number 3 axis. So this is what we got. Okay, so that's the initial rotation out of 3. That's sort of the conceptual power of the Euler angles, as you're thinking of any arbitrary orientation comes about through a sequence of 3 pure rotations about axes. So now we've done the rotation about the number 3 axis. So here's the 3 axis rotation. We did it. Okay. Now we've got this new set of coordinates, the A1, A2, A3, and next we will rotate about the new number 2 axis. Right? I'll put new in quotes, 2 axis. That means the it's A2. Okay, so let me try to draw what I had below for A2. Got A1, A2, and A3. And I'm rotating the body now about the number 2 axis. I guess I'll use red. So there's going to be a rotation, right-hand rule. My thumb pointing in A2 direction, my fingers curl in the direction the rotation is happening. The angle we called that was, let's just remind ourselves again. This is, yaw was psi, then pitch is theta, and roll will be phi. Okay, yaw, pitch, and roll. So this is the rotation rate, theta dot. And that's taking us to a new intermediate frame. So we'll call that the C frame. So this is A2 equals C2. This angle is theta, and then A1 will have moved a little bit too, to a new direction, C1. So that's a C, it's not an E. Okay, and we write the angular velocity. So now this is the rotation rate of the C frame with respect to the A frame, theta dot, and we could either write the A2 direction or the C2 direction. I'll just write C2. And then to remind ourselves, remember C equals the rotation matrix for this rotation, the A directions. And what is this? This is a rotation about the number 2 axis through an angle theta. So writing it out, C1, C2, C3 directions equals, and I always have to look this one up. What's a pure rotation about number 2? It's not as obvious to me. So there's a cosine up here, 0, the negative sign over there. And then there's a 1 in the middle. And then this is sine and cosine. And this is A1, A2, A3. All right. So now we've got this second step up here, this number 2 axis. Now the final one is we'll do a final rotation about the new number 1 axis. And so the new number 1 axis would be this one here. It's the new number 1 axis. So the final rotation is about the, it's now new number 1 axis, which is what we call it C1, but it'll also be the body fixed frame axis, which is B. Okay, so now let me try to draw down here a sketch of the, this is the C1 direction. And where was C2? It's the same as A2. And then where is C3? Okay, now we're going to the body fixed frame by rotating, doing a final rotation about the number 1 axis. So B1, right hand rule, my thumb pointing in this number 1 axis direction, my fingers curl in the direction of a positive rotation. And this angle roll, we're using phi for that. So the rate is phi dot. And this is taking us to say our final location for, oops, all the axes. So this is B3 through an angle V. It's hard to draw here, but we'll write, here's B2. This angle is also phi. Okay, so to write this final angular velocity, the angular velocity of the B frame with respect to this kind of intermediary C frame is, it's got a rate phi dot, and the direction is, we could write it as B1. Okay. And remember, again, the B frame directions equals a rotation matrix times the C frame directions. And this rotation is a rotation about a number 1 axis through an angle phi. So now writing all of that, B1, B2, B3 equals, the number 1 direction stays the same. And then this is cosine phi, negative sine phi. sine phi cosine phi. Or no, that's opposite. This is a positive, and down here is a negative. Okay, and then this is times C1, C2, C3. All right, so the total angular velocity would be the sum of these three angular velocities. Yes, so there was a question, does the final rotation matrix relate to the sequence we're rotating it? Yes. So that's where you get these 3, 2, 1 that we talked about last time. The sequence does matter. So the final rotation matrix would be relating the B frame down here to the original A frame. So you could kind of work out what that rotation matrix is going to be. It's going to be this matrix down here times the C directions. But what are the C directions? It's this matrix times the A directions. But what are the A directions? The A directions are this matrix times the inertial directions. So the sequence does matter. But right now, we just want to know what's the total angular velocity. So the total angular velocity, we use the angular velocity addition formula. So this means what are we looking for here? The angular velocity of the B frame with respect to the inertial frame. With respect to the I frame. It's a sum by the angular velocity addition formula. So if you remember that, we just sort of start adding things up. So we went from the I frame to the A frame, and then from the A frame to the C frame, and then from the C frame to the B frame. So we add all of those up. Okay, and what is it? It is, the way that we've written it in terms of three different basis vectors. Got A3, C2, and B1. So this down here is psi dot A3 plus theta dot C2 plus phi dot B1. And here's what we want to do. We want to actually write this in terms of something that's B1 plus something in B2 plus something in the B3 direction. So we want to write all of it in terms of the B frame components. I'm just putting stars just because it's unknown what those are right now. Right, and this will be our omega 1, omega 2, omega 3, written in B frame components. This one is done. We've got phi dot in the B1 direction. Great. Now we just need to write C2 and A3 in terms of the B directions. The, what do we have up here? We've got the relationship between the B and the C directions up there. I'll just copy it here. The B directions equals pure rotation about phi times the C directions. And we can invert that. C equals, because the inverse of a rotation is just the transpose. So this is R1 phi as a matrix transpose. This is just to remind ourselves that this superscript T means transpose of the matrix, okay? Times the B directions. So what does this give us? This tells us C1, C2, C3 equals, and now I'm doing transpose of this highlighted matrix down here, which is easy enough for me to do. really, all this really does is move where that minus sign is up there. So I've got minus sign and then sine phi, cosine phi times B1, B2, B3. Okay, so from this, I want to solve for what is the C2 direction. What's the C2 direction? Well, from matrix multiplication, I get, so C2 equals cosine phi times B1, now B2 hat, minus sine phi B3. Okay, so I would just plug this expression up here. And then I've got C2 written in terms of the B basis vectors. I could do the same thing for to solve for A, right? Because C equals R2 theta times the A directions, which implies combining with what I know up above, that the B directions equals R1 phi times R2 theta times the A directions. Right, okay. I invert this, I'll get A equals R2 theta transpose times R1 phi transpose B directions. And if I solve for the A3 component, what do I get? So A3 equals, it's a longer expression, negative sine theta B1 plus sine phi cosine theta B2 plus cosine phi cosine theta B3. So this is my expression for this A3 up here. I've now written A3 in terms of these B basis vectors. So yay. I plug all of that in. And I can write the angular velocity, and I'll just collect terms, B1 terms, B2 terms, B3 terms. So here is, what do we get for B1? The B1 component. And then there'll be something else, collecting terms for the B2 component. The main thing now is the process, not necessarily the details of what these are, but the process, because you would have to do this calculation for each of the 12 different types of Euler angles if you wanted to know them all. I'm doing this one because it's a common convention. In fact, some people will just say they're using Euler angles and they'll mean that they're using yaw, pitch, and roll, and they won't tell you that because maybe those are the only ones they knew about. Okay, so we've got this final term, this B3 term. Sine phi theta dot, it's the B3 component. Oh, okay, there we go. So then this term is omega 1. This term is omega 2. That's what defines omega 2. It's in the B2 direction. It's the B2 component of omega. And this is omega 3. So we'll just write this and summarize this in matrix form. And I'm going to use shorthand because it gets tiring to write sine and cosine. So I'll just use S And by S, I mean sine. And by C, I'll define that to be cosine. So we've got omega 1, omega 2, omega 3. And remember, these are the B-frame components. So we put our little subscript B down there. And now this is going to look like a matrix times the rates of change of the Euler angles. So we've got psi dot, theta dot, and phi dot. And what's in here? Negative sine theta, 0, 1. And then we've got sine phi, cosine theta. And then this middle entry here in the center, cosine phi, 0. This is cosine phi, cosine theta, negative sine phi, and then this is also 0. Voila, we've got a matrix. Remember, this is a matrix. We're going to give this a name. This matrix, because of the way it's listed in a table that I will give you, we'll write this as the B matrix. And we'll emphasize it's a function of the Euler angles. We'll write the Euler angles as a vector theta. And this is, in fact, the inverse of that matrix, just by convention. And so this is, just to remind us, note, this is just, this particular form is just for the 3, 2, 1 Euler angle convention. So you would get something else if you wrote it another way. So we've define a vector of Euler angles. We'll call it theta, the little vector sign on top. And so this is theta 1, theta 2, theta 3, where the first rotation is through the theta 1 angle, and then the next rotation is through the theta 2, and the final rotation is through the theta 3 angle. I'll just write over here. So for the 3, 2, 1, we've been using as theta 1, theta 2, theta 3, we've been using yaw, psi, theta for pitch, and then phi for roll. Okay, right, so the first rotation is about psi, and the second rotation is about for the pitch, third rotation is the roll. Okay. So if we were to write this compactly, we would write this as the omega vector written in the B frame. And these time rates of change would be, we would write this as theta, the vector with an over dot. Let me just write that again. So written more compactly, we've got omega, the angular velocity is a matrix, and we're calling it B theta inverse times theta dot as a matrix. If you take the inverse of this, because that's how you'll want to do it, then you get the Euler angle rates as they change in time equals this B matrix. This was, so we found the unknown matrix, at least for the 3, 2, 1 convention. And it's a function of the Euler angles. Some of the entries are 0 and some are 1, but the others are functions of the Euler angles. Okay, so this is just writing the same relationship, but in 2 different ways. So we have a different B matrix for each Euler angle convention. And we'll call these, this thing that's got the rates of change, this is what I called up above, the kinematic equations. So we'll call this the kinematic differential equations of rotation. Because you get omega from the dynamics, but if you want to then know what is my orientation, then you need to solve this kinematic ODE to get the rotation. So I think I showed you last time a sheet that had the rotation matrices C for each of the 12 conventions, and it also has these B matrices. So let me show you that again. And it is, I've placed it in the where I place things. Okay, here it is. Yeah, these are the various Euler angle transformations. So this is showing, this writes things in terms of theta 1, theta 2, theta 3, this theta vector that I was talking about. And so these are the conventions for the C matrix. That's the rotation matrix. And then here it writes what the B matrices are. So we just did the 3, 2, 1. Where is it? 3, 2, 1. It's down here. So if you recall, we got this matrix here for the 3, 2, 1. This is B inverse. And then if you actually take the inverse, well, this actually does it for you. And so this first column is B, the second column is B inverse. Okay. So you've got what you need for all of the conventions. So there is something to note here. All of these B matrices, they'll have like a 1 over and then some either cosine or sine of some angle in front. And that leads to problems. What do I mean? It leads to problems. Well, for the Euler angles, well, what are we writing? We're writing kind of theta dot equals this B matrix times the omega vector, okay? And this B matrix often has out in front 1 over sine of or cosine of one of the angles. And then, you know, times the rest of the 3 by 3 matrix. This leads to trouble because what if that angle, in this case, went to 0? If that angle went to 0, sine of 0 is 0. So you've got 1 over 0. So you have this B matrix numerically blowing up. And this is it's a known problem with the Euler angles. So we'd say that this matrix numerically, an entry just goes to infinity or just blows up. It's not well behaved as theta I goes to 0. So we say that it has a singularity. A singularity, a mathematical singularity, is like 1 over x as x goes to 0. Well, you get 1 over x just goes to infinity. And you can't really define 1 over x at 0, at x equals 0. So you can't define this thing at that angle equals 0, which means the Euler angles work almost everywhere except at a few angles. But if your orientation goes through that angle, you will have problems. And if you're, let's say you're designing a controller for some complicated drone or something, you don't want it blowing up numerically. and then this thing just crashes and fails. So this is a well-known problem. So often for practical purposes, other things are used, things called quaternions. So this is a known problem. It's maybe it's called the singularity problem of Euler angles. I mean, don't get me wrong, they're still useful. They're just not like numerically stable. Go to they give singularities. They give numerical problems at some angles. And that's just life. So alternatives are used, which we don't talk about in this class, but it is good to be aware of them, especially in computer graphics. But I want to think in terms of like a control system. You'd want a control system that's well behaved and doesn't make anything crash. So alternatives are used. Quaternions. So you may have heard of quaternions. Or things called Euler parameters, which are also better behaved. But Euler angles are just so nice conceptually that we like to use them. And these other things, these alternatives, are all kind of based on that principal axis and principal angle that I talked about last time. And I'm going to say some more about those. The principal axis and angle. So it turns out, and I'm just going to write like I did for last time, that C matrix, which when we put all the superscripts in there, I mean C relating the inertial frame to the B frame. When I say turns out, there's a bunch of math that is being skipped for clarity, okay? So it turns out that the time derivative of the C matrix, so just think of this over here is the time rate of change of each of those 9 entries of the C matrix. This equals, I'll write it this way, it's something related to the angular velocity times C, where this angular, I'm writing omega tilde, this is a matrix. It's the cross product matrix, which is a good thing to memorize if you haven't, right? You take the entries, and we're talking omega here is the omega vector viewed in the B frame. So omega 1, omega 2, omega 3. We take those 3 numbers and then we populate entries of this skew symmetric matrix. So we have this equation. This is a matrix ODE. Which means it's actually 9 ODEs. So it's 9 scalar ordinary differential equations. And it doesn't have any problems. It's not going to give you singularities. So that's the advantage of it. But it's 9 ODEs, whereas this thing up here, this is only 3 ODEs. It's 3 nonlinear ODEs. Maybe we can even make that distinction. It's 3 nonlinear ODEs that have a singularity. So it has problems. Where here we have 9 scalar, and they're linear ODEs. It's linear in the entries of C. So we'll say it has no problems. Well, it at least has no singularity problems. In fact, you might call this is the most fundamental kinematic equation of rotation. Kinematic differential equation of rotation. And the axis, the principal axis and angle is actually based on this fundamental kinematic differential equation of motion. And I think I've missed something here. Sorry about that. There's a, just for reasons of convention, there's a minus sign. So time rate of change of this C matrix equals negative omega times C. Everything is changing in time, right? C, all the entries of C are changing in time. The omega vectors changing in time due to dynamics. So we've got this, right? So the principal axis and angle is based on this fundamental equation. And remember, what did we call the principal axis and angle last time? We called them A for the axis and phi for the angle. And we're just going to combine these. We're going to combine these into a single vector. Which maybe has a name, doesn't really matter. I'm going to call it gamma, and gamma is the angle times this unit vector for the axis. Okay, so we've got this. And if we were to view what this signifies, so here's a rigid body kind of seen in its rigid body frame. And in its frame, we've got gamma. It's just some vector. And this vector evolves in time. So again, I'm gonna just have to say turns out, because that would be another whole class. Turns out the time rate of change of this vector gamma equals the omega vector. So that's interesting. It's some vector whose time rate of change is instantaneously the angular velocity. So we might think of this as changing in time. So here is gamma at some initial time, and then this is, we're just kind of tracing out what does the tip of that vector do. It changes with time. So here we are at some later time. I think this makes the most sense if you think of pure rotation about an axis and nothing changing. So think of the case of pure rotation. By pure rotation, I mean you're rotating about a single direction, and that direction is not changing. So here, let me just sketch that case. We've got the body, which is always tends to look like a shoebox or a brick, and got our gamma vector is phi times a hat. Let's draw what a hat is. A hat will be just this unit vector there, and it's a, if the axis is fixed, so we're doing rotation just about one axis, but then the rate of change, or we've got an angle phi that is changing, and what do we have? We've got that omega is phi dot times a. That's how you would write the angular velocity. The angular velocity is a rate of change of an angle and a direction, times a hat. And according to this ODE out here, so this is another way of writing the kinematic differential equation of rotation. If omega here equals d by dt, of gamma. And if A is fixed, then A hat is a constant. Then gamma is just some vector pointing in the direction of A, as we've shown it here. But in general, with omega changing in time, yeah, A is a constant and V dot is a constant. Here, this would be what you get. This is the case, just a schematic for the case of omega not equal to a constant. It's actually changing. So you'll get gamma moving around. All right. How do we relate this gamma vector to the C matrix? Well, we've got something up above that we've written. D by dt of C. So the time rate of change of this rotation matrix equals negative omega tilde times C. And now we'll just substitute in this up here. So this is negative d by dt of gamma tilde times C. So this matrix, or this, yeah, this matrix ODE is solved by C equals the exponential of minus gamma tilde, where we use all the same approach, right? If we have gamma as a vector, got gamma 1, gamma 2, gamma 3, then we can construct a 3 by 3 matrix gamma tilde because it's equal to gamma, the cross product equivalent matrix, okay? So this just means C equals, going back to up here, how do we define gamma? So this is C equals the exponential of minus the principal angle and then the principal axis, but now written as the as this 3 by 3 matrix. So this is what we started with last time. When we talked about the principal axis and angle formula. Okay. So now we've got, right, we've got kind of gone full circle. Now you can hopefully, if you follow the steps, you could see where that axis and angle came from. It's kind of a nice, pretty way to write a rotation matrix. So there we are. The main takeaways for you are that you can write the angular velocity in terms of time rates of change of Euler angles, but they're related through this matrix that has the instantaneous Euler angles. So this this is the relationship. So don't think that omega 1 equals the Euler, that the omega vector equals the time rates of change of the Euler angles. They don't. That's what makes rotation kinematics more challenging, because you have to pick a convention for your Euler angles, and then you have to have the right B matrix. So that is the main takeaway. So if you were solving a problem and you were able to get how omega changes as a function of time from the dynamics, so dynamics gives omega as it changes in time, then you could get the Euler angle as a function of time, or the set of Euler angles as a function of time. And that's kind of equivalent to either having the matrix that relates the two frames, or the principal axis, an angle, or however you want to do it, other things. You take other classes that talk about rotations or how to computationally deal with them for purposes of doing control algorithms and things. Maybe Quaternions would be used, so on. Okay. Now we need to go back to, okay, how do we get the dynamics in the first place? In general, it'll be something that you solve numerically once you've set things up properly. So we're going to talk about the, I guess, the simplest case. What do I want you to do right now? I want you to recall, I think it was lecture, it was actually the 10th lecture, and that was on 924. And we had a way that we wrote the rigid body. We wrote the rigid body dynamics. I'll just write it this way. We had this, if you remember, plus I'm writing the rotational dynamics, or Euler's second law. We have this cross. This is the vector cross product, the moment of inertia times omega 1, omega 2, omega 3. Everything's in the B frame. And then this equaled the moments on the body about whatever our reference point is. In this case, we were using the center of mass G. Let me put a subscript B there. So hopefully you recall that. This is this was Euler's second law. This is the rotational dynamics equation. Differential equation. And it's got these omega 1, omega 2, omega 3. So it ends up being, it's 3 nonlinear ODEs for the omega vector. Okay. And we will look at, I guess we'll look at a simple case of this. We could look at a general case, but I think it's easier if we start with a simpler case. So the simplest case that we will consider is if there's no moment. So that just means these m's over here are all equal to 0. You could say no moment, or equivalently no torque. Or we sometimes write this as the torque free case, or just the free rigid body. That's probably the way it's best known by physicists and engineers. So it just means each of these moments is 0. Where would this case happen? If you're, imagine being out in space. If you're out in space, then and you're spinning or something, then you're a free rigid body. Or if you have some, we take our brick, or we take the space shuttle out in space, and it's a rigid body, to a good approximation, and it's just sort of spinning with no moments. It's a free rigid body. And it's even the free rigid body is kind of interesting because it has dynamics that aren't super obvious. Okay, so that's the simplest case to consider, because then the right-hand side is 0. But then we also want to look in a principal axis frame. if you remember what that was. Use if we use a principal axis frame, so that means the B frame is actually a BP, principal axis. That means that the moment of inertia matrix is a diagonal matrix with diagonal entries only, and everything else is 0. So we'll call those I1, I2, and I3. So then now substitute that up into this, the Euler's second law, and what will we get? We would get, for the first ODE, I1 times omega 1 dot, and then if you work out what this cross product part gives, you can write it this way, I2 minus I3, and it's times omega 2, omega 3, but then, and then the right-hand side equals 0. And you can see this sort of symmetry. This is, we've got 1, 2, 3, right? See, 1, 2, 3, 1, 2, 3. We basically just do a cyclic permutation of numbers 1, 2, and 3. So that means that here we have I2, this is the second ODE, omega 2 dot minus, and we shift everything over 1. So we move the 3 to here, and then the 1, and then this is omega 3 and omega 1 equals 0. The last ODE is I3 times omega 3 dot, shift everything over again. So where the 3 was, we now have a 2, or no, I guess we don't, we have a 1. We have a 1 minus I2 omega 1 omega 2 equals 0. Notice this pattern of 1, 2, 3, 1, 2, 3, 1, 2, 3. Kind of neat. So these are the equations of motion for the free rigid body written in terms of a principal axis frame. So these are the dynamic equations of motion. Sometimes when people say Euler's equation or Euler's equations, they might mean this very specialized case. Like we could have chosen something that wasn't a principal axis frame and we'd have a bunch more terms, but why not use the principal axis frame? Then you kind of minimize the number of terms you have. So this is what we get. These are a, right, what are we trying to solve for? We're trying to solve for omega 1, omega 2, and omega 3. So if you look at this, you go, okay, these are 3 nonlinear ODEs. There's nonlinearity because, right, to solve for omega 1, so omega 1 dot is going to be some function of omega 2 and omega 3. So because there's 2 things, one multiplied by the other, this is nonlinear. So these are 3 nonlinear ODEs for these omega i's. And just to get a first idea of what we get from this, we'll probably want to make an approximation. We could actually solve it exactly, but we just want to kind of get a general idea of what the motion will look like. Maybe I'll just show you. I'll show you what the motion will look like. Not here. So there's a whole bunch of, oh yeah, this is a Veritasium or something. He's got some cool things. what is this? No, can't show that. Too advanced. Here's a rigid body, just sort of spinning out in space. And so this is the type of motion we expect. This isn't, it's hard to see this in normal life. I guess the best that you can get to is you throw something up in the air, and if you're not tossing it at like Mach 1 or something, you will, you can ignore aerodynamic effects. So if you toss a book up in the air, or don't do it unless you're surrounded by cushions, but you could throw your phone up in the air or your toy thing, and right, that's hard to see. It's doing basically free rigid body motion. And there's another kind of simulation of free rigid body motion. This would be like tossing up my iPhone, but it seemed to start out moving about an axis nicely, and then it does this crazy flip. Like, well, what's causing that? This is just free rigid body motion. There's no moments on this, but you get this kind of chaotic motion, chaotic tumbling. It did a flip, and if you're thinking, oh, that can't be real, they actually demonstrated this. I think they demonstrated this on the this is space station. This is just some weirdly shaped object that they got spinning, and it periodically does these weird flips. This is the well-known instability about the intermediate axis, which we will talk about. This is just another view. Oh no, that one doesn't work. So it's a very specialized case to get something like pure motion about a particular axis. Of course, that's probably what you want in some engineering situations. So this would be like spinning the iPhone. I've got my iPhone, and I've got an axis normal to its face, and I'm just spinning about that axis. So that axis is stable. And it turns out even this axis is also stable. So this is kind of the skinny end. Spinning about this axis is stable. But if I spin about what's called the intermediate axis, that's not stable. All this comes from the principal axis numbers, that I1, I2, I3. Just line them up from largest to smallest. The one in the middle, the direction that corresponds to that, the eigenvector corresponding to that principal moment of inertia, is the intermediate axis. It's the middle axis. It's the one that leads to instability. So here's just another diagram showing that for the phone. The number 2 axis with the intermediate axis. So that is a interesting thing that happens with rigid bodies. And I think you could either start this, but I think I won't. I think I'll just leave it for next time. So we're going to continue with analyzing the free rigid body. There's different specializations that people sometimes do. They sometimes say that 2 of these principal axes are the same, and that means it's a symmetric body. And by symmetric, it means like if you have a cylinder, this thing looks like it has symmetry. That's supposed to be a perfect edge right there, but it's not perfect. So if I have a solid cylinder, this looks like it has rotational symmetry. So if I have a cylinder, and let's say I labeled this direction B3, it doesn't really matter what the other 2 axes are, because this has rotational symmetry about that B3 direction. So I2 is going to be equal to I1. And if you have I2 equal to I1, and this is not equal to, say, I3. If I2 is equal to I1, then that means that I1 minus I2 equals 0. And whoa, what do you know? Up here, we have an I1 minus I2. So if that equals 0, then this implies that I3 dot equals 0. So, I mean, omega 3 dot equals 0. So that means omega 3 is a constant. So that's a approximation you can make, that you've got two of the principal moments of inertia equal. And you don't necessarily need rotational symmetry. If you have a block that has a square cross section, I'll try to draw. Here's a block, kind of elongated. And if it had a square cross section up here, and I'm assuming these have uniform density. That's why all that matters is the geometry. If I had a square cross section, then here I1 would also equal I2 if I have the directions the same. So B3, and then perpendicular or normal to one of the faces is B1 and normal to the other face is B2. So this also is called a symmetric rigid body, because all we're talking about is, are two of the moments of inertia the same? If all three of the moments of inertia are the same, so you would get that if you had like a perfect cube or a sphere, perfect sphere, then you would have all of them the same. And if you had all of them the same, then all these terms just drop out to zero. And that means you could rotate this object with perfect symmetry in all directions about any direction, and I1, I2, and I3 are all equal to constants. So you could get these things spinning about any direction. It'll be pure rotation. But in general, that's not possible. Like an arbitrary object like the space shuttle or my phone have I1 is not equal to I2 and not equal to I3. They're just not equal. So that's kind of the general problem. And I think I'll stop there.